Questions about anything? From last time or anything? Well, we've been playing around with the residue theorem for a while. And today I'm going to do a very simple application of the residue theorem, something called the argument principle. And before I get started, I want to emphasize sort of the similarity between zeros and poles. And it's the basis of why the residue theorem has something to do with counting zeros and poles. Okay, so if f has a 0 of order n at z0, then we know we've played around with the power series. If it has a 0 of order n, then the power series starts with an an term. And we know then that we can factor out the z minus z0 to the nth power. And what's left is a power series that converges for exactly the same z rather, as the original power series does. So this power series has the same radius of convergence as the original one for f. And if we call that, why don't we call this capital F of z? Then that's an n. So we've seen that if f has a 0 of order n, then we can write it as z minus z0 to the n times f of z, where f of z is analytic. And not only that, but f at z0, that would be equal to an, and that's unequal to 0. And it turns out you can go backwards. If f is equal to z minus z0 to the n times an f like that that's non-vanishing at z0, then you can go backwards, and sure enough, you write the power series, and you see it has a 0 of order n. So that's kind of like an if and only if thing. Well, the analogous situation with pole is that f has a... Oh, I want to change this to the... Change the wrong word. F has a pole of order n at z0. That means that f, when you expand it in a Laurent expansion, it has only finitely many terms, and the first non-zero in the negative zone, and the first one would be to the nth power in the denominator. And then the rest of the Laurent expansion would go down to the residue term, and then a regular power series after that. And notice that if I factor out the 1 over z minus a, I'll factor it out as z minus z0 to the minus n power. That would clear all those things in the denominator, and I'd be left with a regular power series. And that regular power series plus dot 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 has a radius of convergence the same as the power series part of the Laurent expansion. And so what we get here, we'll call this one f of z now. And it looks exactly the same as the 0 situation. We have that f of z is z minus z0 to the minus n times f of z, which is analytic, and f of z0 is equal to an, which being the order of the pole, that an is not equal to 0. Okay, so here's a fascinating thing now. And this, too, is an if and only if kind of thing. If I can write f of like that in terms of a capital F, then sure enough, it has a pole of order n at z naught. So it's an if and only if kind of thing. And so the fact that we're going to mess around with, a key observation, if I think about f prime over f, this time I'm going to write n equal plus or minus capital N. And I'm going to write f of z is z minus z naught to the nth, could be plus or minus capital N, times an f of z. And the f of z at z naught is not equal to 0. Okay, a key observation is if I mess around with f prime over f, that's kind of like, that's the logarithmic derivative. Okay, let's calculate f prime. F prime, whether or not n is positive or negative, would be z minus z naught to the n minus 1 time, I'm doing the product rule on the top here. What am I saying? N times the derivative of z minus z naught to the n would be n times z minus z naught to the n minus 1. True whether or not it's a plus capital N or a minus capital N. Plus, product rule, z minus z naught times f prime of z, capital F prime of z. And now I divide that by f, which is z minus z naught to the n times capital F. And something wonderful happens here. A lot of stuff cancels out, and I'm left with this thing, n over z minus z naught. And this thing, which is f prime over f, but f is not vanishing near z naught. So this is analytic. And so, of course, it would be given by a power series. So it's analytic near z naught. And we see that the residue term there is n. So fascinating observation here. The residue at z naught, which is either a 0 or a pole of f prime over f, is equal to n if z naught is a pole of order n. Let's see, yeah, it's equal to n would be capital N at a 0. So it would be equal to the order of the 0 of f at z naught. If z naught is a 0, and if it was a pole, then of course that would be a minus n, and we'd still get that little n, which is minus n, so it would be minus the order of the pole. If z naught is a pole. That's fascinating. And so that leads to the argument principle, which is a way of counting zeros and poles that's kind of surprising that you can do it this way. And this is surprisingly useful in lots of areas of complex analysis. The argument principle. So let's suppose I have a simple closed curve. Gamma. And so here's the picture. There's gamma. And I'm going to have an, functions which are analytic inside and on gamma. So there's an inside of gamma here. And let's do the case where there's no poles. So this case first. The case zeros only. Okay, so in this case we assume F is analytic inside and on gamma. Remember, that just means there's a bigger open set where F is analytic. Inside and on gamma, and has no zeros on gamma. So it's inside and on gamma, and it's important to assume also that F has no zeros on gamma. Then you can count the number of zeros inside by a formula. Then 1 over 2 pi I integral around gamma of this thing, f prime of f, f prime over f, is equal to the number of zeros of f inside gamma. And it's important to add that those zeros are counted with multiplicity. So if something is a double zero, it gets counted twice. And a triple zero gets counted 3 times. Okay, and that's just a straightforward application of this fact that I just mentioned. The proof would be, let's see, that integral would be 1 over 2 pi I times, I'd use the residue theorem, 2 pi I, and the only time that there would be singularities of that function inside the integral would be if the denominator vanishes. And so with those singularities, we'd be calculating the residues at points where the denominator vanishes. And that's exactly the zero set of f. Got to think for a second why that's a finite set. We'll think about that in a second. And notice that the 2 pi i's cancel, and you're left with a sum as k goes from 1 to n of m sub k. That would be the multiplicity of the zero, the order of the zeros. These are the orders. And that's what I mean by multiplicity. Okay, and I claim this is a finite set. AK, as k goes from 1 to, there'd be n of them maybe. Why is it a finite set? What if I had infinitely many zeros in there? What?
Then it's
Why? Remember, there's no zeros on the boundary. So certainly the zeros are not piling up on the boundary. So if they do pile up, where would they pile up? Right. Well, if there were infinitely many of them, they'd have to pile up. And piling up, and I think you are coming to this conclusion here, that if the zeros pile up someplace, then the function has to be identically zero. That's the identity theorem. So this is a finite set because if it were infinite, this is a famous fact you learned in Math 341, that an infinite set in a closed and bounded space would have to have a limit point. If we're infinite, and in the compact so maybe I'll add in parentheses, in the compact set, I should have called this domain up here, why don't I call this orange thing omega, the inside. Okay. So if it was an infinite set in a compact set omega closure, it would have a limit point. It would have to have a limit point. In that closed set. And because the function doesn't vanish on the boundary, that limit point couldn't be in the boundary, because by continuity that would mean that the function would vanish on the boundary. Can't be on gamma because f is not 0 there. So a limit point, maybe I should call it something. How about W naught? It can't be on because f is not 0 there. And so W naught is in omega, the interior. And then the identity theorem would imply that f is identically 0. W naught, what? W naught. Yeah, the limit point, W naught, can't be on gamma because f is not 0 there. If there was a limit point on the gamma, that would imply that you'd use continuity to see that f would have to be 0 there, and it's not. So W is inside omega, and then the identity theorem would imply that f is identically 0. And in particular, we were assuming that f wasn't 0 on the boundary, so that can't be true. So that's the contradiction. I guess that ballooned into a bigger thing than I thought it would. Okay. So that's why it works. Questions about that? Well, next case, f has zeros and poles. And poles, but of course none on the actual curve, but none on gamma. Then you get something similar that 1 over 2 pi I times that integral, same integral. You get the zeros like before, so you get the number of zeros of f inside gamma, counted with multiplicity. And then you get the same thing but with poles, except there'd be a minus sign in front of that one. So this would be a minus that, and instead of zeros, would be the number of poles you'd count, and that'd be counted with instead of multiplicity with order. And that's just because of that observation about the residue and using the residue theorem.
Will you get two terms here, or will you just get one and their sum is the sum? So you can
Well, if the thing is a zero, then you calculate that residue and you get a plus order. If the thing is a pole, then you calculate that residue and you get a minus in order. And when you add up the residues, some are zeros and some are poles. So when you apply the residue theorem, you'd be adding up, instead of over the zeros, you'd be adding up the set of the zeros and the set of the poles combined. So that's cool. Well, you might wonder why in the heck this should be called some kind of counting principle instead of an argument principle, because I didn't ever mention an argument, the angle. So next question is, why the heck would you call this the argument principle? And this is one of the beauties of the subject. Okay, so if you think about, let's think of a little segment in gamma. So let's think gamma k is a short segment in gamma. All right, so my picture of gamma k is going to be a little short thing. It's going to start at A and go to B. Let's call that a gamma sub k. Then f, my function f is going to take that somewhere. And so f would take it over here maybe to an f of gamma k. And that would go from starting at f of A and going to f of B. And remember, f is non-vanishing on that gamma. So this is a piece of gamma here. It would continue on. And f is non-vanishing there. So 0 is not on this picture here. And you know, I mentioned that f prime over f is a logarithmic derivative. And so when you look at this picture, you can't help but think of a log. Since this is it's a short segment, there's going to be a direction. It's going to look basically like this, and I can pick a direction. This direction here maybe is a branch cut for the log function. Log of W. I'm thinking W equals f of z. And so the aha moment here is integral along gamma k of f prime over f dz, that would be the integral along gamma k in this picture. That would be d by dz of this branch of the log of f dz. And so that would be the log of f of z evaluated between f of a and f of b. That's the f, z equals a and z equals b. So I'd get log of f of b minus log of f of a. Okay, and that would be, this first one would be natural log of the modulus of f of b plus I times the whatever the argument of f of b is, minus the natural log of the modulus of f of a plus I times the argument of f of a. Okay, so that integral, this is a lot of, I get a term that's going to go away in the end. I'll explain why. I get log of f of b minus log of f of a. That, I'm going to explain why that term is irrelevant to us. And then I'm going to get plus I, argument of f of b minus argument of f of a. That's an increase in the argument. So increase along gamma k of the argument of f of z. That's the argument at one end minus the argument at the other. And you notice that doesn't depend on the branch cut. I'm going to erase this after I do it. So what would that argument be? It'd be the argument whatever this angle is, and the argument whatever this angle is, and this would be the delta argument right here. And it wouldn't depend on what that branch cut is, because that would be plus or minus something, some angle that's the starting and the ending point, and those would cancel when you subtract it for the delta. So it doesn't matter what the branch cut is. That increase in the argument would be well defined, at least in this very small picture, if that's a small segment. Questions about that? Okay, so I guess I should emphasize this thing does not depend on the branch. On the choice of the branch cut. Okay, that's cool. And so now what do you do if you're going to do if you have a gamma, you're just going to cut it up into little tiny segments, little gamma k's that are short, and you can do this routine, and you add them up. Okay, so let's think about if I sum up the integral around the gamma k's of those little segments. Okay. When you add those up around, I'd get a sum. The real part's going to sum to 0. So the real part sums to 0. And I'll explain why. And then you get plus I times the sum of the increase in the arguments. And why if you think about why the real part sums, it's like a telescoping series. And so they cancel every other one, and the first one cancels the last one. When you go around and start over again, the real part is a telescoping sum. Let's think about it. Let's see. The first one would be natural log of mod f z2 minus natural log of fz1. Then the next one would be natural log of f of z3 minus natural log of f of z2 plus dot, dot, dot. And the last one would be log of f of z n minus 1 minus log of f, no, this would be zn, minus log of f of zn minus 1. You get telescoping cancellation. So this f of z2 would get canceled later on over here. Those two would cancel. And then the next one to cancel would be the z3 further on. This log of z3 would get canceled by the next one over here, etc. And this one would get canceled somewhere along the line, the last one. But the first one won't. I mean, the nth one won't. But this one cancels this one because those are the same. Okay, the real part, they pairwise cancel. You get pairwise cancellation as a telescoping sum. And the last one cancels the first one because those are the same point. Cancels first one because it's a closed curve. I guess this purple one would get canceled by that one. Question about that? Okay, so that's a fascinating thing. What I have here is that the integral around gamma of f prime over f dz equals I times the summation, the increase around gamma of the argument of f. Okay. And now you think about, well, what if I divided that by 2 pi I? So if I divide by 2 pi I, I would get the increase in the argument divided by f divided by 2 pi on the right. If I divide the increase in the argument by 2 pi, that's the number of times f of z spins around the origin. F of z spins around 0 in the counterclockwise direction. So it would be plus if it was counterclockwise. And negative if it was clockwise. In the clockwise direction. As z traces out gamma. Okay, so a fascinating thing now. Here's the new improved version. 1 over 2 pi I integral around gamma of f prime over f dz equals number of zeros minus number of poles and that equals this number of times f of z spins around. So that's the increase in the argument of f as you go around gamma divided by 2 pi, and that's the number of times it spins. So here's my feeling. Here's the feeling that you should have about this. Okay, I'm going to walk around gamma. I'm going to walk around gamma, and I'm going to have a wristwatch that gives me a little dial here. I'm going to stick my f of z as a little arrow right here, like the hand of a clock. That's my f of z. And I look at my wristwatch, and as I walk around, that f of z is going to be spinning around. And I count the number of times it spins around. So a little dial. The f of z dial is like a dial. It's just the vector. I stick the complex number at the center of my watch. Centered, zeroed at the point in the curve. And I count the number of times it spins around. Walk around gamma. Count the number of times f of z spins around. Of course, it's never zero, so you don't have to worry about it shrinking away to nothing. It's always a needle. So it's a needle that gets bigger and smaller as you go around. And total them up. And that'll tell you the number of zeros inside. That's why it's called the argument principle. So let me draw a picture here. When you do that, you get the number of zeros of f. If you're only dealing with zeros. If you've got poles, then you'd also get minus the number of poles. But this often gets applied in the case of just analytic. So let's think of an interesting picture. So here's a gamma. And let's say I have only f is analytic inside with no zeros on there. And let's say f does this. Let's see. I'm going to make it spin around sometimes. Oh, here's 1, 2, 3. That's f of gamma. Okay, so they're going like this, etc. F is never zero on the curve, so the zero here is not on f of gamma. And if I were to look at my f of z, that would be like this thing centered at 0, and it's stand at 0 and point at f of z as f of z of t as you go around. If I were standing at 0, I'd spin around 3 times. So stand at 0. Point to f of z of t as z of t goes around gamma. In that picture, I would spin around 3 times. And so that means f has 3 zeros. Inside gamma. Okay. That's cool. And let's see, how could it have 3 zeros? Well, it could have, what did I learn? It could have 3 simple zeros. That would add up to 3. It could have 1 double zero and 1 simple zero. 1 double zero. That would add up to 3. Or it could have just 1 triple zero. Or just 1 triple zero. But those are the only possibilities. Okay. So you learn a lot just by looking at the function on the boundary and seeing what the argument does. Let's see, I've got a couple of minutes left here. Here's a nice observation. Zero isn't as special as you might think. If I, let's let capital F of z be equal to f of z minus w naught. Then we've said it before, if f of z naught equals, because that would be f of z naught minus w naught, if that's equal to 0, and it's a zero-sum multiplicity, then we say that f of z naught equals w naught with multiplicity m. And then we can do the same thing, f prime of z over capital F of z. Capital F is f of z minus w naught. And the derivative would just be f prime of z. So if you want to count number of times f is equal to something, you can do the same picture. So here's the picture here. I would have a gamma. I'd have my f. I like to think of this as like a sheet of rubber. F takes that sheet of rubber and does something to it. I'm going to draw the, I'll make it go 1, 2, I have the same kind of thing here. This is my f of gamma. Okay, the f is going to hit this stuff. And let's see, if I pick a W naught, let's see, it's going to go around like this, like that. Okay, let's see. If W is out here, it gets hit 0 times. So that would be a big fat 0 over here. So W gets hit 0 times there. If it's in this region here, it gets hit once. All the W's in that region get hit exactly once. With that's multiplicity 1. Everything in this region gets hit twice. Even when you add up multiplicities. And everything in this region gets hit 3 times. So if I stick a W naught in there, it gets hit 3 times. Okay, and so you think of that sheet of rubber as getting smeared around. In the place where it gets hit once, it gets smeared exactly once. And the double spot would be smeared twice around. And 3 times would be 3 times around. Okay, and outside, nothing gets hit. That's kind of interesting. Let's see. What if let's think about this picture. Could this picture happen? I have my gamma here, same old gamma. But then on this side, what could I have? I could have something similar going around like this. But then I'm going to have one go clockwise over here. Okay, so these were going around like this. That would make this have to go around clockwise. And then going like that. So could I have a thing that goes like this? Well, the clockwise one, those would be negative. And of course, you can't hit something negative times. So in this picture, it's important that F be analytic, no poles. But if I was using the argument principle here, I'd realize, how can you hit a point -1 times? This would mean that there must be a pole. Must be a pole inside gamma. So when you're dealing with no poles, then this picture is useful. So I'm assuming that F is analytic and no poles. Then you can do this. I guess I'm running out of time. Next time I'm going to apply this and do something famous called Rouché's theorem, which is a fun thing. Next time, surprisingly useful. It's basically the argument principle with a special picture. French guy, Rouchet. Okay, that's enough for today.